up the next homework. Do next week. Find up to isomorphism all abelian groups of order 15,000. There's some list of these. Today, for this problem and the next one, we're going to talk about how to basically take this apart. But basically, the cool thing is it's going to depend on the prime factorization of 15,000. That's going to be a big, huge piece of the puzzle. In the second problem, suppose I take this direct sum or direct product. This is a finite list of groups, and so it's the same as the direct product. Z60, cyclic order 24, 36, 100, 56, and 48. Find the invariant factor decomposition of G, and find the elementary divisor decomposition of G. These are two ways to canonically write any finite group like this, and I'll show you how this is done. We'll probably get back today. For the next problems, we make the following definition. Let G be a group. We define G sup 1 to be the same thing as G prime, the commutator subgroup. This is, if you recall, the subgroup of G generated by all commutators. Now, you start with G and you look at its commutator subgroup. It's a subgroup of that. Well, now you can take that thing and take its commutator subgroup, and you can take its commutator, and you can just go to town with this. Just keep taking commutator subgroups. So inductively, Gn plus 1 is the commutator subgroup of the nth commutator subgroup. We say that G is solvable if you eventually get to the identity by doing this process. For example, if G is an abelian group, you get to the identity in the first freaking step, because if it's abelian, all the commutators are the identity. Right? I wonder why it's called solvable, but actually, this group holds the key. How many of you, so this is just kind of fun. How many of y'all know the quadratic formula? Oh, please, please raise your hand. Okay, just lie to me, make me feel good. How many of you know the cubic formula? Well, no sin there. They don't really teach it in high school, but it exists, right? Go look it up and you will see why they don't teach it in high school. How many of you know the chordic formula? That one exists too. And it is death on a hot plate, because you do all this yin yang and you turn it into a cubic and then you start over to do that again. It's awful. How many of you know the quintic formula? There is none. I don't mean it hasn't been discovered. It has been proven that there can't be one. And the reason is because S3 for the cubic case, well, S2 for the quadratic, S3, the symmetric group on three things for the cubic case, S4 for the chordic case are all solvable groups. S5 and above are not solvable. So you cannot build a formula in terms of radicals. And that's where the terminology comes from. The connection there, there's no reason you should see that now, but that's kind of for your culture there. For right now, we'll show that G is solvable. If G is solvable and N is a subgroup, then N is also a solvable subgroup. Show that if G is solvable and N is a normal subgroup, then G mod N is solvable. Show that if N is a normal subgroup of G, then G is solvable if and only if both N and G mod N are solvable. Show that any group of order 675 is solvable. And show that if G is a finite P group, then G is solvable. For these, it might be very helpful to use parts A, B, and C. To use more computational D and E. Okay, any questions on that? All right. Okay, so let's kind of pick up where we left off last time. We were talking about, well, we were building up toward the structure of finite abelian groups. So let's do the following here. This is this groovy theorem we had last time, lemma 721. Let G be a group of order P to the N. And if I forget to say it, P will always refer to a prime. then G is cyclic if and only if G contains a unique subgroup order P. Unique subgroup of one. Okay, proof. We showed this last time. That is, if it's cyclic, then it has a unique subgroup order P. And in fact, this just depended on knowledge earlier about cyclic groups. So we're going to go by induction. If the order of P is P, then done. Because in this case, when just have the first power, then G is, since it's in prime order, it's automatically cyclic, right? So that was kind of an easy base case. We now inductively assume that hypothesis holds. For all groups for e to the k with k between 1 and m. And now got to lift up the ladder. We got to suppose the order of G is P to the m plus 1. And we're going to use our strong induction to help us out. In this case, we have that the order of G is P to the m plus 1, and G has a unique subgroup of order P. And we want to deduce that G itself is a cyclic group. So consider the homomorphism. D, G to G, given by by the way, that's a good thing about doing proofs. I caught the error that I had there. I forgot to put in the word abelian. By the way, anybody tell me why at this point I caught the fact that I had omitted to put the word abelian in the theorem? Is this a homomorphism?
G is abelian because then only then could you move the G's around.
That's exactly right. Note B of G1, G2, by the definition of the way that I describe this math, is G1, G2 to the P power, right? Now, here's what I want to happen. I want this to be G1 to the P, G2 to the P, which is phi of G1, phi of G2. Without, as Mint points out, without the adjective of abelian, there's no guarantee that I can make this step here, right? So it's like, oh, Jim, you forgot to write abelian. Right. Consider this as a homomorphism. What's the kernel of this? The kernel of this is everything in G that when you take the p power of it, you get the identity, right? This is actually a little subgroup of order P. How do I know it's of order P? Because there's only one subgroup. Remember, there's only one subgroup of order P, and this is of course a P group, and so that's all there can be, right? There can only be P minus one of these elements, and the P elements like this, including the identity, right? This is a unique subgroup G of order P that we're assuming we have. Now what I want to do is mod out. Notice that phi of G is isomorphic to G mod P. Because, why is this true? We have G mod the kernel of phi is isomorphic to the image of phi, which is the same thing as G mod P is isomorphic to phi of G. So this statement here is basically the first isomorphism. And what is the order of G mod P?
Yeah, this is P to the M.
It is. It is the order of G divided by the order of P, which is P to the M plus one divided by P, which is P to the M. And what's the value here? Well, the value here is now we look at G mod P, that's back in our inductive range, right? Remember our hypothesis that any group of order P to the K for K less than or equal to M satisfies this property. That's our inductive step here. Notice that phi of G has a subgroup of order P. Because of course phi of G has order P to the M. So it has to have a subgroup of order P by Cauchy's theorem, right? And it is unique. By induction, we obtain that this is a cyclic group. Phi of G is cyclic of order P to the M. And now I kind of want to work backwards and pull back from this to show that the original G must be cyclic as well. So G mod P is cyclic of order P to the M. M and is generated by the coset X XP. For some XG. Okay, so this is cyclic, so we'll say that this is the generating coset. Yes.
I'm still a little bit confused about how you got that phi of G is isomorphic to G.
Because this homomorphism here takes everything to the pth power. So the first isomorphism theorem says G mod the kernel of phi is isomorphic to the image of phi. But the kernel of phi is P, and the image of phi is exactly phi of G, right, by definition. So we have that this animal is cyclic of order P to the M. It's generated by this coset. So this coset has order P to the M in the group G mod P. And notice that in G, subgroup generated by X contains P. Right, because G has a unique subgroup generated by G has a unique subgroup of P elements, and this is a subgroup of it, so it has to contain, yes.
So I'm a little confused as to the generated by the coset. Is that because we're talking about like a quotient group? So
Yes.
it's generated by coset for that? Okay.
Yeah, that's exactly right. So this is an element of this thing, and this is notation. This is just the generator of this.
Got it.
Now, I've taken X as the coset representative that lives in G. And if you look at what X generates in G, it must contain P, because whatever X generates has a P subgroup. And there's only one P subgroup in G, and it must be contained in here. And so what does that leverage for us? Right. Well, X must be P to the M plus one. And why is that? Because XP to the P to the M power this implies that X to the P to the M is in P. X to the P to the M is not equal to 1. Therefore, X to the P to the M to the P power, which is X to the P to the M plus 1, is equal to 1. So the order of X is P to the M plus 1, and so G is cyclic. So this is a really kind of a nifty theorem because it gives an if and only if on determining if a group is cyclic. I've got a couple of other lemmas that are going to help us kind of come to the fruition with this classification here. When I string the lemmas that I'm showing you together, we will be able to get pretty quickly the decomposition theorem for finite abelian groups that I have bragged is coming. So lemma, the next lemma, right. So And perhaps let me talk about why this one would be important. Let G be an abelian P group. So the order of G is some power of P. And suppose H is a cyclic subgroup of G of maximal order. Then G is isomorphic to H direct sum K for some subgroup A in not an H in G. Okay. What's this all about? Yes.
Can you remind me what a maximal order is?
Yes, I'm gonna tell you that right now. Suppose that the group has order P to the n, right? Would everybody agree that it has to have at least one subgroup of order P, right? That's cyclic. If that is the subgroup, if that is a cyclic subgroup of maximal order, you're done. If not, look at P squared. Is there a cyclic subgroup of P squared? Is there a cyclic subgroup of P cubed, etc.? In fact, it's more efficient to do top down. Suppose a group's of order P to the n. If it's cyclic already, there's your maximal subgroup because the whole shebang is cyclic. Look down to the next step if it's not. Is there a cyclic subgroup of P to the n minus 1? If there is, that's one of maximal order. If not, step down again. Is there a cyclic subgroup of order P to the n minus 2? Continue this process. But by the time you get to P, the ones of order P for sure are cyclic. Everybody agree with that? So at some point, this process, so it's just the largest order cyclic subgroup you can find in there, right? And this is kind of a groovy thing because here's what this means. This theorem means that any abelian, any finite abelian P group is the direct sum of some of copies of a cyclic group. It's cyclic groups in a direct sum. How do you know that? Start with G. Suppose it's forward P to the n. Suppose this is, say, a P to the m, right? And it's a maximal cyclic subgroup. What's left over is a P group. Everybody agree with that? Now do the same thing to K. It's got a maximal cyclic subgroup, right? Break that up into two pieces. Look at this piece. It's got a maximal, and break it up. This process will terminate because G is a finite group, right? So what's implicit in this lemma is now we know that any finite abelian P group can be written as a direct sum of cyclic groups. So that's a cool observation that this will give us here. So once again, we're going to go by induction on the order of G. We're going to go by induction on the order of G, which I will say notation is P to the n. If n equals 1, then done. Let me also point out that if G itself is cyclic, we're done. But let me just be clear about that. If G itself is cyclic, then the pieces parts here would be G is isomorphic to G direct sum identity. Everybody agree with that? So that's what it would be. So this is trivially kind of true if G itself is cyclic, so we can usually assume not to move forward. So let's assume that the result holds for all abelian P groups of order P to the M or less. So inductive hypothesis. Inductively, we assume those holes for all abelian P groups of order P to the M or less. And again, I'm going to build my inductive ladder. Check this out. What happens for groups of order P to the M plus 1? So here's the deal. Now suppose the order of G is P to the M plus 1. We want to show that this works. If G is cyclic, then done. So we assume not. What do we know happens if G is not cyclic? What was the characterization from lemma 7.2.1? If we assume that this G is not cyclic, then what I know is I have at least two subgroups of order P. Everybody agree with that? That was the big thing about lemma 7.2.1, is you can tell whether a group's cyclic or not just by seeing whether or not it had one or more subgroups of order P. G has at least two subgroups of order we're going to exploit that. Let H be a cyclic subgroup of maximal order. H and G be a maximal cyclic subgroup of G. And let me emphasize that this exists, because what you can do is we already know that we're assuming that G is not cyclic. So just count down. Is there a cyclic subgroup of order P to the M? If so, then I'm going to pick that to be my H. If not, is there a cyclic subgroup of order P to the M minus 1? And just keep going down. And at least by the time I reach P to the 1 power, there have to be cyclic subgroups. So let H be such a maximal cyclic subgroup of order G. And call it something. With the order of H. And what do I know about K? Well, K. K has to be at least 1, because I know that any subgroup of order P is cyclic. So you're not going any smaller than 1. And it can't be any more than M, because if it were bigger than M, it would have to be M plus 1. And we know that we're assuming that G is not cyclic itself. So the maximal cyclic subgroup can be at most P to the M. And notice this H here, because it's of order P to the K, it has to contain a subgroup of order P. Agreed? And remember, this thing has at least two subgroups of order P. So I'm going to pick let K be a subgroup of order P such that K is not contained in H. And again, lemma 7.1, H is a cyclic group, so it contains only one subgroup of order P. There has to be another one that can't be contained in H. Okay. Any questions so far? So now I'm going to do some yin yang with kind of the second isomorphism theorem. So let me point out first that I'm going to write my groups additively here. Right? Because this is a P group and we picked it to not be in K, right? So the intersection of H and K is 0. And so here comes the second isomorphism theorem. If you look at H plus K mod K, on the second isomorphism theorem, this is isomorphic to H intersect K, which is isomorphic to H, because that is 0, right? And so have an arbitrary G and G, if G is in G, then the order of a coset G plus K divides in, well, H plus K mod K, just for emphasis, must divide the order of G itself. This is a consequence of one of your homework problems, where if you have a homomorphism from G somewhere, then the order of the image of G must divide the order of the original G itself. And of course, the order of G well, it's P of K, isn't it? And of course, the order of G, since G is an element of G, well, G generates a little cyclic subgroup, right? And whatever the order of that cyclic subgroup is the order of G. But H is the maximal cyclic subgroup. So the order of G is no more than P of K, right? So cyclic subgroup hence the cyclic subgroup H plus K mod K, which is isomorphic to H by the above. Of course, since they're isomorphic, since H is cyclic, this is cyclic, has maximal order in G mod K. Has maximal order in G mod K. And the order of G mod K is less than the order of G, so we can apply the inductive hypothesis. So by induction, there exists, say, N mod K from G mod K, such that I can break this up into a direct sum. G mod, K is isomorphic to H plus K mod K, direct sum N mod K. That's what the inductive hypothesis allows us to do. And so this means that when I put these groups together, H plus K plus N, I have to get all of them. And this is actually the same thing as H plus N, right? And the reason this is the same thing as H plus N is because K is contained in N. So really the K here is superfluous because everything in K is contained in N. So this is the same thing as H plus N. So G is H plus N, where N is the group from G that's the preimage of that quotient group. Also, N intersect H plus K is equal to K. Right, because the intersection of these two groups, for it to be a direct sum, has to be trivial. So that means essentially this intersect this can only be things that are equivalent to the identity. So that intersection has to hold. And if this is the case, then so H intersect N actually must be 0. And that is the death knell here. So what we have is we have G is this plus this, and the intersection is 0. Therefore, G H direct sum N. And this is the conclusion that we wanted to come to. Okay, any questions so far? Let me give you the next one. I want to probably skip over this a little bit so I can get actually into doing some computations for y'all. I'll talk you through it anyway. There's one more major thing in a corollary, and then I'm going to give you the breakdown. Proposition. Proposition 17 group. Let G be a finite abelian P group. Then G is uniquely a direct product of cyclic P groups. Direct product or direct sum doesn't matter because it's finite of cyclic P groups. Here's basically the way it works. This is again kind of induction. So by induction on the order of G, which is P to the N. So let me clear induction on N. N equals 1, you're done because this is it has to be cyclic, right? So there you go. Assume it's true for all exponents up to m. Now look at g to the m plus one. If it's cyclic, you're done again. If not, then by the previous lemma, there is a maximal cyclic subgroup, right? Break it off into a smaller piece and now apply induction to the piece that's not cyclic and just go down from there. That was basically the way that I described it when we started off here. And uniqueness isn't so hard to see either. See if you can figure that one out. Here's a corollary that's worth recording. This is wildly untrue in general for finite groups, but for abelian groups, this is a nice little result. Any finite abelian group is a direct product or sum, because we're talking finite groups, of its CELO P subgroups. I'm just gonna, so this one you can also do by induction. So I'm not gonna do a full proof here, but I'm gonna do the heavy lifting part. Need kind of a sketch of this. True if order of G equals P to the A. Because all of G is its own CELO P subgroup, and there you go. That's all G is its own freakish CELO P subgroup, and that's it. So there's nothing to show here, right? If A Q to the B, where P, Q distinct primes, and A, B natural numbers. What happens here? Well, this is the heavy lifting part. It's the two CELO subgroups part. Generally, what we're going to do is go by induction on the number of different primes that divide G. That's a finite number. Here I've got the two case. If I show you how to do the two case, the rest of it is pretty much exactly like this. So here's what I'm going to do. Let P equal the CELO P subgroup. And of course, the order of P is little p to the A. Right? And I'm going to let capital Q equal the CELO Q subgroup. So here the order of Q is Q to the B. Everything okay so far? Now, notice that if I look at PQ, this is an old, well, actually, let me do this first. It'll be best for me to do it first. Somebody tell me what that is. Yeah, it's the identity, right? Because anything that lives here has to have order power of P. Anything that lives here has to have order power of Q. And the only thing that is both a power of P and a power of Q, since they're different primes, is the zeroth power, right? So this is the identity. And I write it that way since I'm assuming these groups are abelian. But actually, so far, this is all hunky-dory, right? Also, this is back from the old first or second isomorphism theorem. This is the order of P, the order of Q over P intersect Q, right? So. Okay, so far. And there's one final thing. So here's what we got. I know that PQ is all of G because I can count the elements. This thing right here is all of G. That also means it's a subgroup of G, but there's no shock there. 2, P intersect Q is the identity. Right? And finally, P and Q are normal in G. This is the only piece where I actually needed the groups to be non-abelian. I don't really need them to be non-abelian. I just need this normality condition. But here we go, right? I get this for free. Therefore, G is isomorphic to the direct product or direct sum, whatever you like, being Q. And that's it. The induction, the steps now beyond this are pretty easy because you just add in primes and all these conditions hold. Okay, any questions on it? Yes.
For number 3, we didn't get that from the work. We just got that for free, right?
This comes from Billion,
Oh, okay.
right? So all the subgroups are normal. Okay, any questions on that? Okay, so let me give you this last, so here's the big theorem that I have promised. And I probably don't have time to do any computations for you right now, but we will jump into that next time, but I'm going to give you the statement here. So this is the big kind of classification theorem, if you will. 725. Suppose that G is a finite abelian group of order n. Well, let's take this first. G is finite abelian, and the order of G is n. Then G can be decomposed uniquely as follows. Number 1, G is a finite direct product of groups of prime power order. Cyclic groups of prime power order. So number 1, you can decompose G into a product of cyclic groups, all of prime power order. I looked at my notes. I did not say cyclic in the notes, so I'll try to remember to make that. But that's important. And 2, there's another way to do it. Well, actually, there are many ways to do it, but these are 2 canonical ways. This one is called the elementary divisor. Decomposition. Number two, G can be decomposed into a direct product sum, well, of cyclic groups. G isomorphic to C1 direct sum, C2 direct sum with direct sum CK. Where each of these are cyclic, each CI is cyclic of order MI, and M1 divides M2, divides M3 all the way up to MT. This is called the invariant factor decomposition. And these are called the invariant factors, and MT is equal to the exponent of G. So these cyclic, these orders, cyclic orders that divide one another, smallest to largest, these are called the invariant factors, and the largest invariant factor is the exponent of G. There are special cases where the elementary divisor decomposition is the same as the invariant factor, but usually they're different. And we're actually going to get our hands dirty and work on this on Monday. Any questions? Well, y'all have a good weekend. I will consider doing the math club. Might be of interest. I'll let y'all